Number 29, this is a good one. How many 4 permutations of the positive integers not exceeding 100 contain 3 consecutive integers k, k plus 1, k plus 2 in the correct order? Well, a 4 permutation of the positive integers. Let's just see how many of those there are, first of all. Right? So, I can put any positive integer from 1 to 100 in this slot, this slot, this slot, and this slot. This is not the correct answer, by the way. I'm just showing you guys how many of those there are, right? So there's 100 times 100. Right, maybe let's make these parentheses. Right, times 100 times 100, right? And so that's, each of those is 10 squared, so that's 10 to the second times 10 to the second, or really just, 10 to the 8th, right? Yeah. And 10 to the 8th is 100 million. So there's 100 million permutations of the positive integers from 1 to 100, or rather 100 million 4 permutations. And one of those looks like this. Or rather, I shouldn't really do the set. I should do the block of 1, 2, 3, 4. And I'll explain why I do blocks later. But yeah, basically one of those could be 1, 2, 3, 4. Another one could be 92, 7, 4, and 1. Maybe put commas just in so you can be a little more clear. But there's a lot, right? And we want to get a subset of this giant set of 100 million, right? And we're not going to use the number 100 million in this problem. I just want to show you guys like how large the set we're going to be taking from is. So if we get a fairly large number, don't be surprised. So let's start off with what we know, and we'll see what we can do with 4 numbers multiplied together, right? We're going to get something that looks like this. This is how you get a permutation, right? Not really this sort of thing, right? This is a permutation of 100 taken 4 at a time. Rather, we're just going to take a permutation of 100, right? And we're going to do it, what we did just a second ago was this. Again, sorry, I'm not really getting to the problem yet. I just kind of want to explain that. Right, or rather, anyway. So I'm getting a little off track, but let's get back to the problem. So, you've got 4 spaces, right, for your block, right? And how many, for any given block, you have 4 spaces, and how many possible numbers can I put in here if, according to the rules defined by A, where these consecutive integers can perhaps be separated by other integers in the permutation, and it also has to contain the 3 consecutive integers k, k plus 1, k plus 2, and then I like to call this last element z, right? Call whatever you want. And so there are, for the kth spot, how many possible things can we put in there? Well, we can put from 0 to 100, right? Well, you can't put in 100 because that would make this number here 101, and we're not allowed to do that. We're only allowed to do 0 to 100. So really, you only have what options for k? Well, you can do 1, you can do 50, you can do 98, but you can't do 99 or 100, right? So you can do 1 to 98, right? So 1 to 98, right? And that's 98 choices, right? So 98 for k, and then k plus 1, if you've got something in k, right, k plus 1 is already determined, right? So you only have, excuse me, you only have one option for k plus 1 for every given k. Rather, let me say that again. If you have a defined k, you only have one option for k plus 1, right? So, how many options then would you have for k plus 2, right? Just one, because k defines k plus 1 and k plus 2. That is to say, if you choose a k, and you would stick by the rules of this whole block here, right, then you're going to have to say that there's only one option for k plus 1 and k plus 2. For every block like this, there's only one option for k plus 1, there's only one option for k plus 2. Just trying to clarify that point. And then how many options are there for z? Well, you've got remember, you're originally picking from the positive integers from 1 to 100, but you've already used up 3 of them. So 100 minus 3, 100 possible options minus 3 options that you've already used. Remember, you can't you can't use 2, 3, 4, 3 because why can't you do that? I don't think it's allowed. I really don't think in this sort of problem that's allowed. I don't think Z here can be a repetition excuse me again, of anything in these first 3 boxes, I guess, right? Or these 3 spaces. I don't think Z can be a repetition of that. So, here, let me just get a blank slate again. So how many options do you have? You have 98 times 90, or rather times 1, and then 100 minus 3 is 97. Right? And so, right, this is a permutation, so does order matter or does it not matter in a permutation? Well, you could say that order does matter in a permutation, and this is the way I remember it. You can say order does matter in a permutation because a permutation has a lot more possibilities. And if order matters, then you're going to have a much larger set of possible combinations, right? Whereas if you just took 4 elements like 1, 2, 3, 4, and you said order doesn't matter, well, then you've covered this whole possibility. Whereas if you said order does matter, you could do 4, 3, 2, 1. You could do 2, 3, 4, 1, and suddenly the set of all these possible combinations increases in size by a significant quantity, right? So permutation order does matter, right? That's why this is a 4 permutation rather than a 4 combination. I'm trying to work out this problem as well. This is fairly difficult. So order does matter, therefore you cannot use k plus 1 or k plus 2 for your zth for the z entry here, right? So if I get 1, 2, 3, 4, or if I get 1, 2, 3, I can't use 2 again, or I can't use 3 again, or I can't use 1 again. This is 98 times 1 times 97, right? And so we're not done quite yet because there's a few other things we have to account for. But let's just do this math really fast. 98 times 97. This is going to give us 9506 possible combinations for the 4 permutations where order does matter, right? Where you have a k plus 1, and a k plus 2, or rather, this is going to give us the 4 permutations for k for a set that has a k plus 1, and a k plus 2, right? If a set has all 3 of those and a z, right, then there's 9,506 possible combinations of that kind of a block. Right, here's the block. Anyway, so now that we've gotten that, right, there's a few other things we have to account for, right? 1, have we really counted every possible combination? What was it again? 9506. You've gotten 9,506 combinations. But remember, we had 100 million, right? So are we done? Well, we might be. Let's test a block to see, what we can do. 1, 2, 3. We'll just do 1, 2, 3, 5, right? Because when you start doing 1, 2, 3, 4, we haven't talked about that yet, but that's another thing we're going to have to talk about in later part of the problem. So let's do 1, 2, 3, 5. 1, 2, 3, 5 is an example of this kind of a thing where you have a k plus 1, a k plus 2, and a z. Right, and how many ways can we order this given part A, which says the consecutive integers can be separated by other integers in the permutation. They don't necessarily have to, which means that 1, 2, 3, 5 works. But it can also be 1, 2, 5, 3. It could be 1, and I'm listing these out for a reason, 2, 1, 5, 2, 3, and 5, 1, 2, 3. So for every one of these 9,506 combinations, you have 4 combinations, you have 4 choices for that. So 9,506. Let's do this times 4. Let's do this like a matrix, right? So if you have 9,506 columns and you have 4 rows, right? Then for every column here, right, and here's a row. There's only 4 rows, but there's 9,000 of these columns, right? Here's the 9,501st, second, 9,503rd, 4th, 5th, 6th, right? You've got all these to account for, right? There's 4 for every, or there's, I don't even know how to say it, but 4 times 9,506 will give you this total in here, right? And this is all this giant box here. That's actually what we want to count. So what's 4 times 9,506? It's 38,024.
Why are you at David's?
Because I'm using his iPad. Okay, so this is like the large set that we needed. This is a fairly large possible number of combinations, right? So we have this giant set of, I just kind of want to, draw circles for a second, right? We have a lot of these. We have 38,024 of them. And so we might have a few duplicates, right? So now let's check for duplicates. So how do we really do that? Well, let's do some example ones, and let's see if we can find any duplicates. Let's do 1, 2, 3, 4. Remember this nice simple thing? Well, okay, let's list out the possible combinations of 1, 2, 3, 4. You have 1, 2, 3, 4. You have 1, 2, 4, 3. Right? You have 1, 4, 2, 3. See how I'm just moving the 4 over to the left one, and then 4, 1, 2, 3. Okay. But what about see how 1, 2, 3 is the k plus 1, and k plus 2? What if the k plus 1, and k plus 2 came from the 2, 3, 4? Right? And your 1 was your z. Right? What if that was the case? Well, then you would get 1, 2, 3, 4 would be duplicated. Right? What would be the other combinations of this one, just for fun? Let's just do it. 1, 2, 4, 3. Wait a minute. Is that right? Perhaps we separated. Yeah, I don't see why not. What is it? 2, 4. Oh, right. Sorry. So let's actually do it as the set of, because that was really confusing. 2, 3, 4, and 1, rather than that. And so 2, 3, and 4, and 1 goes to. It also goes to 2, 3, 1, and 4. As well as 2, 1, 3, and 4, and 1, 2, 3, and 4. Here's the 2, 3, 4, and 1. Here's the top one. And so see how when you introduce something like 1, 2, 3, 4, where you have k plus 1, k plus 2, and you have k plus 3 in there as well, whenever you have this special case, you're going to have one duplicate made when you take all the combinations of them. There's going to be this one special combination that you simply cannot have. So if we have a duplicate every time you take k plus 1, and k plus 2, and k plus 3, then how many duplicates do we have? Well, let's just. The easiest way for me to do this is just to count them out, because I couldn't think of a better way to really do this problem. Right, that's a minus sign. Other than just counting them out, on a future problem in a test, if you can figure out some sort of trick, great. But if not, you can always resort back to counting. So let's just count out the duplicates that we know of. 1, 2, 3, 4, 2, 3, 4, 5, right? 3, 4, 5, 6, 4, 5, 6, 7, all the way up. Let's do a dot, dot, dot. To 97, 98, 99, 100. Is 98, 99, 100, 101 possible? No. Even though it's a k plus 1 through k, or k through a, even though it's a k through a k plus 3, it's not even possible because you can't have 101. So there's this many duplicates, right? Well, let's just see if we can count these really fast. How many there when we start with 1? How many are there when we start with 2? There's 2. How many are there when we start with 3? There's 3. Well, if we go all the way up to 97, there's just got to be 97 duplicates, right? So let's subtract off our duplicates. Let's see what we get. Remember, the correct answer is 37,927. You can check that in the back, and that is what we get. So that's how you do this kind of problem. Let's go on to part B. So let's start over, right? Let's rather than thinking like, okay, now that we got part A, let's go into part B. Let's just start back over from the beginning because that's the easiest way to do this. So let's look at it again, right? How many possible for this one? Well, you have 98 possibilities for that one. You can't use 99 or 100, but you can use every other positive integer. How many for this one? Only 1. How many for this one? Only 1. And how many for this one? 97. Right? Again, it's a permutation, so you can't use... it's a 4 permutation of the positive integers. And what I'm guessing is that a permutation of the positive integers does not have repeats. I'm going to assume. So I don't think you can repeat something. So anyway, otherwise everybody's explanation of this problem would have been wrong that I looked up. So anyway, 98 times 97, that's a large number. What was that, 5,040? 9506, right? And so let's look at a element within this 9,506 again. Let's look at 1, 2, 3, 5. Yeah, let's look at 1, 2, 3, 5 again. This block here. Again, it helped us out last time. We could do, remember last time we did 1, 2, 5, 3, and 1, 3, or 1, 5, 2, 3, and 5, 1, 2, 3. Well, now, or rather, let's write those out. Right? Is that allowed? Where they're in consecutive positions in the permutation, that is not allowed. Right? 5 is interrupting the consecutiveness of k plus 1, and k plus 2. Right? What about 1, 5, 2, 3? That's not allowed either. Right? What about 5, 1, 2, 3? Well, that's allowed. Right? So for every one of these blocks, you have a second one that's also allowed, but you don't have 4 like you used to. Remember the last time we multiplied all this by 4? Because there were 4 combinations per block, or there were 4 no, I don't want to say duplicates. There were 4 choices per block. Well, this time there's only 2. So we're going to multiply by 2, but I have an odd, strange feeling from doing this problem before that we're still going to get these duplicates at k plus 1, k plus 2, and k plus 3. So let's check. Is 1, 2, 3, 4 within this set? I don't see why not. You certainly can have 1, 2, 3, 4. And if you have this block 1, 2, 3, 4, that means you're going to have a duplicate of it, right? And we can show that by putting together the element 1 and the element 2, 3, 4, right? And or putting the block, really. It's, kind of confusing, bear with me. Or you could put together the block 1, 2, 3, and 4, right, to make this block up here, right? And so both of these are valid, but they come out to the same answer, which means they're going to be a duplicate, and we don't want that. So how many of these do we have? Well, first off, let's do 9,506 by 2. Let's see what we get, and then we'll subtract how many duplicates we have. We get 19,012. And we're going to subtract what our duplicates are. 1, 2, 3, 4, 2, 3, 4, 5. Look familiar? All the way to 95. Let's do 90, 96, 97, 98, 99, 97, 98, 99, 100. Right? And so you have 97 duplicates. Right? Just like last time. And that's going to come out to 18,915. Right? And that's the best explanation I can do at the moment, but that is the correct answer. Yeah, good luck.